All right, let's do another famous form. Now, that's the main goal of this video, that and a little bit of practice. But we can start with some review and an overview of some famous forms. Now, at the risk of spending more time than we may need, let's review everything for those who may need it. Logic is the study of methods by which we determine whether the premises of an argument provide good enough support for their conclusion. In deductive logic, we're interested in whether the premises guarantee the conclusion, meaning is it possible for the premises to be true and the conclusion false at the same time? If it is possible, the argument is not what we call valid. If it's not possible for the premises to be true and the conclusion false at the same time, the argument is valid because it has that special quality, validity. Validity means the characteristic of an argument such that its premises cannot be true and the conclusion false at the same time. Now, validity in logic is a technical term. In the dictionary, you might find any number of uses for the word valid and the word invalid that are not strictly speaking what we're doing in logic class. In logic class, we're talking about a very specific thing that we just name validity, a very specific attribute of an argument that we refer to by saying the argument is valid. This is a technical term, not necessarily a dictionary term. All right, so the two basic systems of deductive logic, basic strategies of deductive logic, basic branches of deductive logic are categorical logic and statement logic. In deductive logic, to test arguments for validity, what we want to do is break the arguments down into their parts so that we can then more easily see what is the pattern of the argument, what is the way the argument is reasoning about things, what is the structure or the form of the argument. And in categorical logic, we break an argument down into one kind of small part, and in statement logic, we break an argument down into another kind of small part. In categorical logic, we break it down into the small parts that are its terms. In categorical logic, in proposition logic or statement logic, we break an argument down into the small parts, which are its atomic statements. All right. Let's see. First, let's clarify the vocabulary. Proposition and statement are synonyms. So proposition logic and statement logic are synonyms. And now here's some more synonyms. Atomic statement and simple statement, those are synonyms. Complex statement, compound statement, molecular statement, those are synonyms as well. So a simple statement or an atomic statement is a statement that's not made of any others. A rookie mistake to avoid, one I've made plenty of times in the old days, a rookie mistake to avoid is thinking that a simple statement is a statement with just one statement in it. And a compound statement is a statement with two or more statements in it. It's a perfectly ordinary mistake. But consider the negation. A negation is a denial of a statement. So here's a statement. There is a full cup of tea here. And here's another statement. There is not a full cup of tea here. Unfortunately, that's the one that's true. The denial is true. So the statement, there is a full cup of tea here, is an atomic statement, a simple statement. It's not made of any other statements. But when I say it's not the case that there is a full cup of tea here, or there is not a full cup of tea here, I'm denying that atomic statement. So my denial is made of that which it denies. There's the statement, there is a full cup of tea here, and then there's the denial. It's not the case that there's a full cup of tea here. The denial statement is made of the other statement. The negation is made of the thing negated. So a negation is considered a compound statement because it's made of another statement. An atomic statement is one that's not made of any others. A compound statement is one that's made of one or more atomic statements. And now it's even closer to being completely tragically empty. All right. So in statement logic, what we want to do is break down an argument into its atomic statements and everything else. The everything else is things like the not, the if, the then, the and the or. And also the if and only if, but we'll worry about that later. In proposition logic or statement logic, we break down an argument into its constituent parts, specifically the atomic statements, and into everything else, and we look at the relationship among those atomic statements to see if the relationship is such that this is an argument whose way of reasoning about things makes it impossible for the premises to be true and the conclusion false at the same time, in which case the argument is valid. And we'll be able to see that more easily by looking at the pattern of the argument by breaking it down into its smallest parts. Pretty much that's all we do in proposition logic. The rest is just details and strategies for doing that well. One very good way of doing it well is what we can call the famous forms method. Now, this will not work on just any statement. This will not work on just any argument. It only works on an argument that has one of the famous forms, one of the famous patterns of argumentation. And it's still a very good method. You can't use it on just any argument, but you can use it on a lot of arguments, and these are arguments that people use a lot. And it's a really good training exercise for everything else in statement logic, so let's do it. In the famous forms method, we learned several famous argument patterns. Some of them are valid, some of them are not. And any argument using one of those valid patterns is a valid argument. Anyone using one of the invalid patterns is invalid. Well, almost certainly. You do have to get the most specific pattern of the argument you can. You have to correctly you have to correctly break the argument down into its smallest statements and the relationships among them, and then identify the pattern of the argument by looking at all that. It is possible that you could have a valid argument that uses one of these invalid patterns if you didn't look at the form specifically enough, because as I've explained in earlier videos, an argument has more than one pattern. It's got a very simple pattern, premise, conclusion, or premise, premise, conclusion, or premise, 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 conclusion, depending on how many premises there are. And then it's got a more specific pattern, like one of the premises will say, if X, then Y, and another premise will say X, and the conclusion will then say Y. So there's the generic pattern, premise, premise, conclusion. There's the specific pattern, X, if X, then Y, X, therefore Y. One of those is a valid pattern, one of them's not. So it's possible to have a valid argument that uses an invalid pattern, and every valid argument does have at least one invalid pattern, namely premise, premise, conclusion, or however many premises there are. And it's possible that once in a blue moon, you might find an argument using an invalid famous form, but it's actually a valid argument because of one of the details, one of the very specific details of the argument. But you won't run into any trouble there if you do a good job representing the argument. If you do a good job looking at the argument according to its smallest parts, in this case, it's atomic propositions. Let me mention one more thing that I don't think I've mentioned in this video yet. Those are the basic systems or the basic branches of deductive logic. It is possible to break down an argument into its parts and look at its terms and its statements at the same time. That's a strategy or a system or a branch of deductive logic we call predicate logic, and I'm not likely to get to it in this series. I don't enjoy it very much. All right, so where was I before I had to explain all these other details? I think I was about to summarize the famous forms method. The famous forms method is pretty simple. Look at the pattern of an argument. Sorry, I break an argument down into its small parts to identify the pattern of the argument, and then just look to see whether it's one of the famous form patterns. State that it is, state which pattern it is, and then if it's one of the valid patterns, say the argument's valid. If it's one of the invalid ones, say the argument is invalid. Now, there's a certain number of famous forms, and I don't know what the number is because some are a little more famous than others. And when you're doing the famous forms method, obviously, the more famous forms you learn, the more arguments you can use them on. But the harder it is to keep track of all the forms and to keep them memorized and not get confused. Constructive dilemma versus destructive dilemma, hypothetical syllogism versus disjunctive syllogism, and modus ponens versus modus tollens versus denying the antecedent versus affirming the consequent. It can get confusing if you have a lot of forms to keep track of. But if you have fewer forms and they're easier to keep track of, you can apply them to fewer arguments. So there's some balancing act here. Now, here is a set of the famous forms I would like to keep track of. If you're taking a logic class, your teacher might require you to keep track of a different number of famous forms. Do your best. Here's my set of famous forms I like to work with. First, modus ponens. If P, then Q, P, therefore Q. Now let me explain this. The custom in logic class is to use lowercase italicized letters to symbolize any proposition, but to use uppercase, not italicized letters, uppercase, not italicized letters to symbolize specific propositions. So if I were going to symbolize the argument, if it's raining, then the grass is wet. It is raining, therefore the grass is wet. I would symbolize it with something like if R then G, R therefore G, and R and G would be capitalized. But if I'm looking at the pattern, the generic argument pattern of P then Q, the generic argument pattern modus tollens, I would symbolize it as if P then Q, P therefore Q, where P and Q are lowercase and italicized, meaning only that there are millions of arguments, probably billions, trillions, actually there's probably an infinity of different arguments. Any possible proposition could fit into this. There's an incomprehensibly large number of arguments that fit this pattern. And when we symbolize the pattern, thus, if P then Q, P therefore Q, we're symbolizing all of them together. They all fit this pattern. P and Q stand for any proposition that fits into a modus ponens argument, not a specific argument. We'll probably see more of this shortly. Let's look at the other patterns. Modus ponens, modus tollens, and denying the antecedent and affirming the consequent are all related. If you have an if-then statement, if A, then B, if X, then Y, if P, then Q, if one thing, then another thing, what you can do is you can say if one thing, then the other thing, first thing, therefore the second thing, or if one thing, then the other thing, not the second thing, so not the first thing either. But it's a mistake to say if one thing, then the other thing, definitely the other thing, therefore also the first thing, because sometimes you can have the other thing without the first thing. If P, then Q, P therefore Q, that's what we call the modus ponens pattern. That's a valid one. Here's the modus tollens one. If P then Q, not Q, therefore not P, that's another valid one. But here are two invalid ones that are invalid because sometimes you can have the then, you can have the second thing without the if, without the first thing. If one thing, then the other thing. Sometimes you have the other thing, but not the one thing. If P then Q, not P, therefore not Q, invalid argument. If P then Q, Q, therefore not P. If P then Q, Q, therefore P, invalid argument. Now, the examples will make this so much clearer for most of us. If it is raining, then the grass is wet. Take that as an if-then proposition, and then either affirm or deny either the if clause or the then clause. I should probably have a then typed up here, shouldn't I? If it is raining, then the grass is wet, and either affirm or deny either that it is raining or that the grass is wet in your second premise. And two of those are good moves, two of them are bad. Example, if it's raining and the grass is wet, it's raining, therefore the grass is wet. It's not possible for these premises to be true and this conclusion false at the same time. Valid argument. If it's raining, then the grass is wet, the grass is not wet, therefore it's not raining. It is not possible for the premises to be true and the conclusion false at the same time. Good argument. If it's raining, then the grass is wet. It is not raining, therefore the grass is not wet. It is possible for the premises to be true and the conclusion false at the same time. That makes this an invalid argument. For example, what if it's true that if it's raining, then the grass is wet, and yet the grass is wet and it's not raining because it rained an hour ago and it hasn't dried up yet because it was there was a lot of dew this morning at sunrise and it hasn't all dried up yet, and it's still just 15 minutes past sunrise. Or someone was washing a car near the grass, or there were some sprinklers on. These things happen. If it is raining, then the grass is wet. The grass is wet. Therefore, it's raining. Again, for the same reasons, an invalid argument. So let's go down to this one. This is what we call the hypothetical syllogism argument pattern. If P, then Q. If Q, then R. Therefore, if P, then R. Here's an example I used for the kids, which seems outdated now and may seem irrelevant to you, depending on who you are, where you live, et cetera, et cetera, et cetera. For Hong Kong Disneyland, this made sense when I gave them this example. It was probably somewhere in 2021. If the virus slows down, Disney opens. If Disney opens, we shall rejoice. Therefore, if the virus slows down, we shall rejoice. That's a hypothetical syllogism. It has the pattern if P, then Q, if Q, then R, therefore P, then R. It's not possible for the premises to be true and the conclusion false at the same time. And it is the year 2022. And this video will probably come out in 2023. And I don't even know if this will seem like a timely example or not. But here's an argument pattern. Here's an argument that has the pattern disjunctive syllogism. Either DeSantis will win or Harris will win. Harris will not win, therefore DeSantis will win. Here's another one. Either DeSantis will win or Harris will win. DeSantis will not win, therefore Harris will. Now that is a valid argument, and what both of them do is they have an either one thing or the other thing. You take away one thing and therefore you're left with the other. If the premises are true, the conclusion has to be true. If it's true that either one or the other, and it's not this one, it's got to be the other one, right? That's how this works. And it doesn't matter which one you take away. So either P or Q, not Q, therefore either P or Q, not Q, therefore P is a good argument. Either P or Q, which hand is P, which hand is Q? Either P or Q, not Q, therefore P. Either P or Q, not P, therefore Q. Those are both valid argument patterns. But here is an invalid pattern. Either P or Q, P, therefore not Q. Or either P or Q, Q, therefore not P. This we could call the affirming a disjunct pattern, and it's invalid because sometimes you can have both P and Q. Now, occasionally, you may be talking about something where you can't have P and Q at the same time. In fact, either DeSantis will win or Harris will win. DeSantis will win, therefore Harris will not win. That's not a bad argument. And it's not a bad argument because there's an unstated premise. The unstated premise is they can't both win at the same time. So if you encounter an argument like that, it's not explicitly said, not both. If it says either P or Q, not P, therefore Q, but if you see an argument that says either P or Q, P, therefore not Q, and the argument doesn't explicitly say they can't both be true at the same time, but you know that they can't both be true at the same time, and anyone making this argument could reasonably assume that, then assume that it's what we call an enthymeme, an argument with an unstated step. Just write in the extra step, they can't both be true at the same time. Then your argument's valid, no problem. But the argument, as stated, if it's the whole argument, either P or Q, P, therefore not Q, is invalid because sometimes P and Q can be true at the same time. Here's a good example. And if you don't like these examples, whatever, find your own political examples or your own examples of anything that makes sense. But politics is a good one because it frequently happens that one politician running for office against another politician, they both have problems, and sometimes they're both jerks. So here's a bad argument. Either Trump is a jerk or Biden is a jerk. Either Trump is a jerk or Biden is a jerk. Trump is a jerk, so Biden is not. Yeah, that's a bad argument. Either Trump is a jerk or Biden is a jerk. Biden is a jerk, so Trump is not. Yeah, that's a bad argument. They could both be jerks. These things happen. Okay, so if you don't like the example, whatever, just pick your own. Now, let's see. Here is a constructive dilemma pattern. Now, originally, there's a new famous form, the constructive dilemma pattern, and we want to learn the form and then practice with it with a scheme of abbreviation momentarily. The original constructive dilemma argument that inspired this was something in a Dilbert cartoon where, if I remember correctly, Ashok the intern ended up saying, truly we are doomed either way. But I couldn't keep all of that in my head, or didn't, I don't know, I wanted to come up with a new example that was sort of inspired by this, and it sounded terribly depressing. This example might not work for you in that you might not accept all the premises, but whatever. Any number of, probably most of us will actually accept the premises. We might not think an election was stolen, but we often will think, whether it's in 2016 or 2020 or 2024 or one of those other years, we'll think that the people voted for the wrong person who was also a jerk. We think this happens, right? Almost all of us think this happened with at least one of these elections. So either P or Q. If P, then R. If Q, then S. Therefore, either R or S. Let me illustrate that with hand motions there. Either P or Q. Either P or Q. P, Q. If P, then R. If Q, then S. Therefore, either R or S. Either the election was stolen or the people actually voted for that jerk. If the election was stolen, we have a problem. If people actually voted for that jerk, we have another problem. Therefore, either we have a problem or we have another problem. And as Ashok the intern might have added, truly we are doomed either way, which would be an extra step on top of that, which is fine and leaves a valid argument, but it's a slightly more complex pattern. Let's not take the truly we are doomed either way step. All right, so either one thing or another thing. If the one thing, then a third thing. If the other thing, then a fourth thing. Therefore, either the third or fourth thing. That is a good argument pattern. We call it constructive dilemma. Let's leave this politics example and go to Socrates' example from Plato's Apology, my favorite example for constructive dilemma. Now, Okay, let's summarize what a scheme abbreviation does. With deductive logic, we want to break down an argument into its parts. And with statement logic specifically, we want to break down an argument into its constituent atomic statements. And then we want to restate the argument using those statements, using those symbols, rather. And that will let us look more easily at the argument pattern, which will tell us whether the argument is valid or invalid. And when it's the famous forms method, it will let us see whether we're dealing with one of the famous forms. We'll be able to name the famous form. And then say the argument's valid because it's a constructive dilemma form in this case, or it's valid because it's a modus ponens form, or it's invalid because it's an affirming the consequent form, or something like that. So I'm mentally rehearsing a few things I don't want to lose track of. Let's see. Let me state this more formally. Here is what the scheme abbreviation system does. The scheme abbreviation strategy, not system. The scheme abbreviation strategy allows you to test arguments for validity in statement logic or proposition logic, in statement logic or categorical logic with the maximum possible accuracy and clarity and hopefully ease and hopefully speed. No need to waste time on this. With the scheme abbreviation, you do, let's say, three things. One, give a scheme or a legend for abbreviating the statements. I'm going to rephrase that. One, give a key or a legend for symbolizing the atomic statements in the argument. And if we were doing categorical logic, we would give a system, a scheme or a legend or a key for symbolizing the terms in the argument. Rewind and watch categorical logic videos if you need to. Okay, so let's start this again. One, for schemes of abbreviation in statement logic and specifically famous forms method. One, give a key or a legend or define your symbols, a key or legend for symbolizing the atomic propositions in the argument. Two, restate the argument using those symbols. Three, identify any famous forms and state whether the argument is valid based on which famous form it is. So in this case, we've got 4 atomic propositions, and we're actually going to have 3 premises. And here is an extra step we can use if we need to. And if my brain holds up, I'll add an extra step. An extra step at the end. I'm filling in the template. That's the word. I'm filling in. No, I'm making a template here, and we can fill in the details later. Later, I'll have to select one and delete the other for valid, invalid. Now, I'm actually going to do valid because this is a scheme abbreviation practice for a constructive dilemma specifically. So we know it's going to be valid, but you don't normally know that going into your famous forms exercise. All right, so I might give an extra step somewhere around here to clarify things further. Let's not do that yet. Let's go back to schemes abbreviation and fill in some unnecessary substeps that might help a lot, namely underline the atomic propositions. Our first atomic proposition is there is life after death. It occurs twice. And just to make this funner, let's color code them as well. But actually, I think it increases clarity as well. And we'll color code our symbolization as well to make it clear how everything connects. If there is either there is life after death or death is the end of experience. If there is life after death, then death is the gateway to another life. If death ends experience, then death is still nothing to worry about. Therefore, either death is the gateway to another life or death is still nothing to worry about. You can already see the constructive dilemma pattern. Either there's life after death or death is the end of experience. If there's life after death, then death is the gateway to another life. If death ends experience, then death is still nothing to worry about. Therefore, either it's a gateway to another life or death is still nothing to worry about. It's good to see the relationship, but let's Show the relationship. Don't just see the final result, demonstrate it using the right method. That's what we're practicing here, demonstration using the right method. Let's make this second atomic proposition red, shall we? So our first atomic proposition is there is life after death. It occurs twice and it's phrased the same way both times. Our second atomic proposition is death is the end of experience. It occurs twice. It's not phrased the same way both times. So you're just going to have to pick one. They mean the same thing. Death is the end of experience. Death ends experience. They mean the same thing or close enough for our purposes. In a basic logic class, you don't want to care about any distinction between these two if you can find a distinction at all. Don't get distracted by it. It's a waste of time. Those are the same atomic propositions. That's how the argument is designed. Death is the gateway to another life is our third atomic proposition. It's going to occur twice. Let's make it green. And then death is still nothing to worry about. Occurring twice is our fourth and final atomic proposition. Let's color it purple, brown. I feel like using brown. So this color coding system, I think, will help a few people. It won't help everyone. I hope there's enough shading differences between these different versions of, I guess, grays, if you're colorblind. Let's see. You know what we could do? We could underline, italicize, and bold some colors. Like we could bold the blues, if that would help, and italicize the reds. But this is not a perfect system because I've got 4 atomic propositions here. Let's see. Bolding blues, italicizing reds, and I can remove the underlining on some of these. If I remove the underlining on the browns and keep it on the greens, I got nothing. I don't have a 4th formatting option. I could increase the font size slightly there. So I hope this will, no, not 16, font size 15. I hope this will be slightly helpful to who's colorblind and trying to watch this. There. So blue, blue bold, red italics, brown larger font, green underlining. Those are our atomic propositions. Now this is the first step, and we still haven't finished it because I haven't actually written it down yet. There is life after death is our blue bold one. Our red italics, death is the end of experience. Green underlining is death is the gateway to another life. And bold, bigger font is death is still nothing to worry about. And now, since I'm just filling in a template here, I have to obviously fill in what capital letters I'm going to use to symbolize these atomic propositions. Now, it's totally okay to just do W, X, Y, Z or A, B, C, D, but it's usually good to choose a capital letter that has some connection to the atomic proposition, as long as you don't get confused. Don't use D for this sort of argument because the word death occurs in all of them. I like to use L for life after death and G for gateway and E for end of experience. And I guess N for nothing to worry about. So yeah, that'll be my system. So now I've done step 1 of the scheme of abbreviation practice. I've symbolized the argument. I've defined my symbols. I've said how I've explained what my symbols are symbolizing. L, E, G, and N are symbolizing, respectively, the atomic propositions. There is life after death. Death is the end of experience. Death is the gateway to another life, and death is still nothing to worry about. L, E, G, N. So now, my first premise is either L or E. Either there is life after death, or death is the end of experience. My next premise is if there is life after death, then death is the gateway to another life. See how that's going to be written? If L, then G. Next premise, if death ends experience, then death is still nothing to worry about. That's if E, then M. If death is the end of experience, then death is still nothing to worry about. Conclusion, therefore, either death is the gateway to another life or death is still nothing to worry about. Either G or M. Now here's a really minor issue that might confuse 1 out of 100 people. I say therefore in the original argument and so in the symbolized argument. It doesn't matter. Therefore and so are synonymous. They're both conclusion indicators. Logic class anyway, they're synonymous. I'll switch one so to therefore. So here's our symbolized argument. Now I've done step 2 of our practice with the scheme of abbreviation. Either L or E. If L, then G. If E, then N. Therefore either G or N. And at this point, you can scroll down and forget everything that came before. And you can hopefully just look at it and see this is a constructive dilemma argument pattern. And that tells you it's valid. And you're done. That's it. Now, let me see if I can clarify one thing, because I think this will confuse some people. It took me actually years to get a proper understanding of what's going on with these letters. Okay, so let me add one extra step that might help some of us. This is the symbolized argument, either L or E. If L, then G. If E, then N. Therefore, either G or N. But the constructive dilemma argument pattern doesn't look quite like that. The constructive dilemma argument pattern is either P or Q. If P, then R. If Q, then S. Therefore, either R or S. And you might be thinking, why the heck do I have L, E, G, N all capitalized up here? But I'm saying this is a constructive dilemma pattern, and the constructive dilemma pattern is P, Q, R, S, all lowercase and italicized, not L, E, G, N capitalized, no italics. What's up with that? You might be thinking, oh, I don't care. I can tell it's the same pattern. And you're thinking pretty well if that's what you're thinking. But you can go a little bit further and understand what's going on here. I think I've said this before a few times, but this is confusing enough that it needs to be said more times. The system we're using is this. When we use capital letters, no italics, we are symbolizing specific propositions, specific atomic propositions. In this case, there is life after death for L, death is the end of experience for E, death is the gateway to another life for G, death is still nothing to worry about for M. When we use these lowercase italicized letters, we are symbolizing any and all propositions. The constructive dilemma argument pattern is literally millions, billions, probably an infinity of arguments that fit this pattern. The lowercase p stands for any proposition, maybe every proposition, probably every proposition, but you have to do metaphysics here. What is a proposition? Are there propositions that no human being has ever thought of? Are there propositions that no person has ever thought of? And does God exist? And has God thought of every possible proposition? All these interesting questions, or questions you think are not interesting at all, depending on what you think is interesting. I think probably there's an infinity of propositions. I think actually God does think of them. But at any rate, there are literally millions of propositions. That's not even controversial or interesting or a metaphysical issue. There's literally millions of propositions that P stands for, and that Q stands for, and that R and S stand for in this pattern. Either P or Q, if P then R, if Q then S, therefore either RS or PQRS or lowercase and italics. Because this is the generic pattern that symbolizes every constructive dilemma argument in existence, including the ones only God has thought of. If there is a God who thinks of things humans have not. I think so, but that's beside the point. There's literally millions of constructive dilemma arguments human beings have thought of, and P and Q symbolize literally millions of propositions. The argument we've symbolized has capital letters symbolizing just those specific atomic propositions, and this whole symbolized argument is symbolizing just one argument, our original argument, this paraphrasing of Socrates here from Plato's Apology. So try not to get confused. Yes, they're the same pattern, and that's all you need to know. That will allow you to go directly from the symbolized argument here to stating this is a constructive dilemma. It's valid and being done. But if you want to know more, try to understand the pattern you're looking for is given in this generic form that symbolizes all arguments, whereas you just symbolized one. And if you need to do more, don't try to symbolize your argument directly into lowercase p and q. Things could just go wrong in so many ways. I won't pause to explain the ways. But here's what you could do. Here's an extra step you could do in the middle that might do you some good and will not likely do any harm. Take your symbolized argument, this extra step. Take your symbolized argument and replace your specific propositions. Because when I have L here, I'm just stating there's life after death. When I have E here, I'm just stating death is the end of experience. Take your specific propositions and replace them with generic symbols for all propositions, but do it consistently. Replace your first one with P, your second one with Q, replacing it every time it appears in the argument pattern. Third one with R, again, replacing it where you find it in the argument, PQRS, and then do the same for the fourth one. And now you should have a perfect statement of the constructive dilemma argument pattern. And once again, you're done. And I'm done. I'm ending this video. See you next time.